Blue cone monochromatism, the other form of achromatopsia. Congenital achromatopsia is a rare inherited condition. It is composed of two major forms, rod monochromatism and blue cone monochromatism. Both forms of achromatopsia can cause four significant impairments: debilitating glare problems, severe color blindness, reduced visual acuity, and nystagmus. BCM is found nearly exclusively in males, in 1 in every 100,000 births. It can occur in females, but the occurrence in women has been estimated as low as 1 in 10 billion. While rod monochromatism is inherited as an autosomal recessive inheritance, requiring the affected gene from each parent, BCM is an X-linked recessive condition inherited from a carrier mother. BCM passes down from the mother, who is a carrier, to the affected child, who is nearly always male. Affected males can only pass it on to their daughters. All daughters of an affected male will be carriers. All sons of the affected individual will not have the condition and will not be carriers. The carrier daughters have a 50% chance of passing it on to their children. The male children receiving it will only have one X chromosome, and thus BCM will be expressed. Females have two X chromosomes. The one unaffected X chromosome from their father is usually enough to prevent BCM from occurring. Those with BCM may frequently have a brother, maternal male cousin, or a maternal grandfather with the condition.
Do you have other family members who have this condition?
My grandfather and I have 3 cousins, males, that have the same condition as me.
Are they on your father or your mother's side of the family?
My mother's side.
Better understand blue cone monochromatism, we must understand the photoreceptors in our retina. Normally, we have both rods and cones that work independently or together depending on the brightness levels. There are 3 basic levels of cone rod function. The photopic, where we use only cone cells. This would be in all bright lighting situations. The mesopic, where both rods and cones function together. This would be a mildly dark area, but where you can still see colors. And the scotopic, where only our rod cells function. This would be in dim light, like a dark, moonless night. Each of the 3 cone receptors has a different light-sensitive chemical that reacts to different colors of light. We have red, green, and blue sensitive cones. All the colors we see come from the mix of these cone signals. In blue cone monochromatism, 2 genetic variants on the X chromosome at position XQ28 result in the failure of the chemical needed to detect red in the red cone cells and to detect green in the green cones. Thus, blue cone monochromats are left with only blue cone receptors and rod receptors. Optical coherence tomography allows us to cross-sectionally scan the fine layers of the retina. Here we see a normal OCT scan. The arrow shows the fovea. Normally, this is the area of our sharpest vision. It is composed of red and green cones packed tightly together. There are no rods or blue cones found in the fovea. Now we see the same scan of a patient with blue cone monochromatism. Notice the arrow pointing to the gap in the photoreceptor integrity line. The gap shows a missing signal where red and green cones would normally reside in high concentrations. This scan predicts the loss of red and green cone cells through the retina. This explains the reduced vision found in all achromats. With only one type of color receptor, blue cone monochromats have severe color vision loss. Some, however, can detect certain mild shades of blue and yellow under the right lighting conditions. This, however, does not mean that they see blue as you and I do.
Right here, from here to here, looks black to me. From about here over to here appears yellow, and then this is blue.
Since our 3 types of cone cells normally provide all of our vision in bright light, loss of the red and green cones results in severe glare problems in bright lighting. Those with BCM are left with only blue cones and rods, and the rods cannot function in bright light. This creates an overwhelming glare, a condition called hemerotopia or day blindness, and is often the most debilitating part of BCM. Here we see the scene of a normal retina. The scene would be moderately bright and in full color. Without special sun filters, the blue cone monochromat would see the scene as overwhelmingly bright and with either no color or some mild blue and yellow visible. Patients must often squint to control glare. Squinting, however, while helping darken the scene, can reduce the visual field. Aversion to light and nystagmus are often the first signs that a child has achromatopsia. Nystagmus is a rhythmic shaking of the eyes that may present at age 3 to 6 months. It is usually pendular and, as in other achromats, may decrease with age.
As a child, did your eyes have nystagmus? Did they shake? Did your parents report that they noticed a shakiness to them?
That's one way my mother figured out that I had some sort of visual problem at that point, or had the visual problem that was in her family. Was when I was a baby, my eyes would, as she called it, quiver or dance, and they would do it quite readily.
Today they don't seem to do that, though. It seems like it's quieted down a lot, hasn't it? There's just a very fine little tremor there.
I don't even notice it myself.
The nystagmus often decreases significantly with time, and there are cases where no nystagmus has occurred. This patient reported nystagmus severe enough for his mother to recognize there was a problem as an infant. Today, at age 49, the nystagmus is very faint. The visual acuity of blue cone monochromats as a group is moderately impaired. The typical range of vision is from 20/60 to 21/20. However, some patients may be as low as 2200. The loss of cone cells in the fovea is the initial cause of reduced acuity, but the debilitating glare problems can overwhelm the patient's vision. Thus, controlling glare is the most crucial step in helping the individual with BCM. The approach, however, is different than in rod monochromatism, where red filters effectively control the glare. In BCM, we must avoid the use of solid dark red filters, as the red will block the blue light entering the eye and further reduce the patient's vision. But red filters are very effective in preventing the bleaching out of the rod photoreceptors, allowing them to function at higher light levels. And blue filters allow the blue light to pass through to the blue cones. The answer is a magenta filter, which is made from both red and blue dyes. Magenta filters allow both the red and blue light to pass to the retina. This allows both the blue cones and the rods to function better in bright light. Here we test a patient with both red and magenta filters.
When I place this filter in, what happens?
It makes everything a lot clearer, what I can see.
And then without it, does it get worse?
It fuzzes.
Now what happens if I put the red filter in?
Then I lose most of it.
And it gets much better back.
Oh yeah. Big difference.
We can provide the magenta filters in either contact lenses or eyewear, and in different shades of magenta to custom fit each patient for inside and outside lighting. If light and glare are well controlled, some with BCM who have only mild visual acuity loss from 20/60 to 20/80 may be able to obtain a restricted driver's license. Those with less visual acuity may be able to become a bioptic driver. Bioptic drivers use special telescopic systems to aid them in driving and require extensive behind-the-wheel training. Blue cone monochromatism is usually a stable condition with minimal change over time.